Hello, everyone. Now that Nell read that out, I realized I didn't give you a fun fact. I gave you Iryna is turning into her grandparents' fact. I think in a couple of years I'll come back here and I'll tell you about all the goats and bees I'm having. Hi, welcome to writing a GraphQL compiler in Rust. My name is Iryna. I am here from Copenhagen, Denmark, where I currently live. I'm running on about 5 liters of coffee, so it's either a good thing or a bad thing. We'll find out. Thank you so much for having me here again. I'm really excited to be here, and that's not just the coffee talking. So a little bit about me. I am an engineer at Apollo GraphQL, and I also garden, as Nell pointed out, but I grow a whole bunch of things. And I also make zines. The zine I've printed out, you might have seen, about proc macros is mine. Please take one if you haven't already. I printed 200 of them at a local Rezo printer in Copenhagen. All those things are fun and nice, but today I actually wanted to talk to you about the thing I've been working on for the past year and a bit called Apollo RS. It's a series of crates that we've put together at Apollo GraphQL, and I'm really, really excited to share a whole bunch of stuff about this project. So without further ado, let's take a look at what we'll actually talk about today. First, I want to give you a little bit of background about Apollo RS, about Apollo, about GraphQL, just to set us on the same page. I want to talk to you about compilers, just in general, so we kind of understand where Apollo compiler comes into play among a whole bunch of other things. I'll talk to you about why we're doing this. Then we'll kind of take a look as to what exactly the compiler does. We'll look at the stages of the compiler process, and finally, my favorite bit is we'll talk about the architecture of the project. So, without further ado, let's take a look and kind of set the stage and get a little bit of background information. The preface. So I think it would be important for us to take a look at what GraphQL actually is. And GraphQL, what it is, it's a query language for APIs. Let's take a look at kind of the schema. The schema defines a bunch of different types, and these types are related to each other and are used amongst different ways. GraphQL has a spec that defines how each one of these types is meant to be used. There's also a spec for validation of these types, and so on and so forth. So it's quite explicit. A schema can also have a query that has relationship to the schema, and it kind of looks like this. Also, the types get reused, and this is kind of the shape of the language, of the query language itself. The next thing that would be good to talk about is about, just give you a glimpse about what Apollo does. And Apollo GraphQL is, as the name suggests, a GraphQL company. And what we do is we build a lot of developer tooling and infrastructure around allowing people to unify their GraphQL app and services. And this should allow people to kind of build on top of their GraphQL. Recently, we've been writing a lot of things in Rust, including some of our critical infrastructure code. So we're joining the Rewrite It in Rust group of companies. Very excited to be here, very nice. But the main thing we do is we work with a lot of GraphQL. But this talk is not really about the things we're rewriting in Rust, but about the backbone of lots of these projects, which is Apollo RS. And Apollo RS is a spec implementation of GraphQL in Rust. And it is spec compliant and just implements GraphQL in general. So this is what we'll focus on today. Apollo RS is a combination of various different crates, a workspace, if you will. It composes of a few important ones. One is Apollo parser, which parses GraphQL query language. The second one is Apollo encoder, which encodes programmatically into GraphQL. We have Apollo Smith, which is a test case generator. It is named after Wasm Smith, a bytecode alliance test case generator for Wasm. Thank you very much to bytecode alliance for such a wonderful inspiration. But all of these things, they boil down to Apollo compiler. We'll focus quite a bit on Apollo compiler and Apollo parser as like the two kind of sibling crates, or the crates that relate to each other. But before we kind of go into that, I want to set the stage of what it is that the Apollo compiler does. And here it will be good to kind of talk about what is even a compiler. Something that we are quite familiar with is we have some C code that compiles down to assembly. And I'm here to tell you that Apollo compiler does not compile down to assembly. I'm sorry if that is disappointing. That would be kind of cool. If anybody wants to take that on, please go ahead. And I think to kind of give a bit of an explanation, because we don't actually compile to any binaries at all, is to look at this tweet from 5 years ago, and I'll call this section Iryna does Twitter review. So look at this tweet by Steve Klapnick, a Steve tweet, if you will. It goes, "You, sobbing, please stop. You can't just call everything a compiler." Me points at documentation tooling, compiler. And while Apollo compiler is not quite a documentation tooling compiler, I think it kind of opens up our mind a little bit about what could it be. And continuing kind of on this Iryna does Twitter review, let's look at this other tweet that I've slightly adjusted for this presentation by Ryan Kavanagh. This is called X is a compiler alignment chart. And it kind of outlines, and I think it is quite funny, but it also kind of sets the stage to think about different inputs and outputs that we can have as a compiler. And while I would love Apollo compiler to be the rebel and be compared to the sun, we simply take in input as text and output instructions. But what does that really mean in the context of GraphQL? What that really means is input for us is GraphQL or Schema Definition Language, or SDL. As our output, we output instructions, but they are in a form of a database. And I promise we'll talk together about the database portion in a little bit. I know I'm kind of teasing you a little bit, but we'll get there. So these are kind of the things that align us on this alignment chart. Input as GraphQL, output as database. And at this point, what you're probably wondering is, why are you going through so much effort for a query language? Why can't you just use the parser or use any given parser for GraphQL, because the GraphQL spec is usually implemented by various parsers? Why are you writing a compiler? Here I want to kind of give you a bit of an explanation as to why we went through so much trouble, really. And kind of as I mentioned before, Apollo works with quite a bit of GraphQL. In fact, most of the tools we write and we maintain have some sort of version, a form of GraphQL in them. And so it's really, really important for us to be able to work with it. Working with increasingly more complex graphs and sitting in a critical position in a lot of people's infrastructure requires us to have a more performant and reliable way to work with graphs and work with documents, work with GraphQL documents even. We might want to do a whole bunch of different things, like compose different graphs together. They're quite complex. We might want to do query planning. We want to perform all sorts of like wild and unique schema manipulations. And all of those things, perhaps, or not perhaps, all of those things are made a lot easier if we have a database to ask these questions from. Questions such as, find me the join directive type. Where is it? What is the type of this field in a query operation? Is this type pet in scope? These are the kinds of things we want to be asking of a database, and writing a compiler in such a way allows us to be able to ask these questions easily. Writing a compiler also, and I will have some water. So having a database and having a compiler produce us a database is great. But another thing that writing a compiler does for us, especially if done in a thoughtful and meaningful way, is being able to provide a really, really good developer experience for people working with GraphQL. So there's that database bit, and there's also this developer experience. And so one of the features of the compiler is to be able to provide a really ergonomic and really usable and easy to use API to this database. It is incredibly important to be able to have something that's ergonomic and is done well. But, and while it's ergonomic and is done well, it is also performant. But if you really think about it, performance doesn't really mean anything unless we have those ergonomics in place. And that is something that we as Rust programmers really understand because we work with Rust-C. And Rust-C is performant, but the one thing we really, really appreciate about it is it's the developer experience and the diagnostics we produce and how the compiler sits there and helps us along the way with the diagnostics it produces. And so one of the things that we would also like to do with the Apollo compiler is be able to provide good diagnostics about a given GraphQL input. And so at this point, I would like to, again, go to a Twitter review. This is officially a Twitter review talk. This is an Esteban tweet, if you will. My steaming hot take is that the primary function of a compiler is to take malformed code and emit diagnostics to help the programmer turn it into well-informed code. A compiler is an error reporting tool with a code generation side gig. And I actually really liked, and this is from a talk that Esteban gave at RustConf in 2020, a really good talk if you would also like to have another talk about compilers. And what I really like about this tweet is that I think the way that we thought about Apollo compiler really fits with this as well, because the one thing that we want to be able to do is, given a malformed GraphQL, we want to be able to provide diagnostics and walk the user as to how they're able to fix this sort of malformed code. And so the design really for Apollo RS is designed in a way where we could replicate that Rust-C experience that we all know and love, but have it for GraphQL. All right, so I've talked to you a whole bunch about kind of why we're doing this, but I think at this point it'll be nice to actually take a look at how this compiler works. So let's take a look at a small demo. We've mentioned two key features that the compiler has. It's the API to compilers database and also really good diagnostics. We'll just focus on the diagnostics bit for this small demo. So, small example, we take in GraphQL, SDL as input, and we run it through the compiler and we validate it. And then at the end, we display diagnostics. Here we use a reporting library by Kat Marchand called Miet, and it produces incredibly beautiful reporting for diagnostics that use all the sorts of information we're able to feed it, and just, it works beautifully. So we'll see it in a demo in a second. So what I'm gonna use here is my colleague's Avery Harnish's CLI, where he hooked up Apollo compiler to a CLI and a web browser. We'll just use the CLI in the terminal to see how the compiler reacts on a given document that's slightly malformed, not entirely right, and we'll fix it together. Okay. This is not made for tall people. All right, so we'll lint and watch the schema. The schema is on the left-hand side, and it's a little bit malformed and has a few things we have to fix. So I'm spoiling this for you a little bit. There's errors. So what we find is that we have 4 different errors, and I will increase this a little bit so it's easier to read. We'll start with this one. We currently have a subscription operation that has 2 root fields. We have a helpful message that we're not allowed to have 2 root fields, so we just have to remove it. We should now have 3 errors. The second error is that we have an operation that is defined twice within a document. Also, another helpful error message, I wonder who wrote these, can only be defined once in this document. So we're going to remove another one of these, because we shouldn't have to. So this should leave us, hopefully, with 2 errors, unless I messed up. Another one is that we have an unnamed operation, which is only allowed if it's only the only one. So what we should do is probably just remove it and just have the one operation that's named. All right, and the last helpful thing that the compiler tells us with this particular query is that we are using a type that is not defined in scope and that we should define it. And so what we can do is define a type result. I'm just making things up, and it'll have a field called HTML that returns a string. And at the end of it all, we have a functioning document on the left-hand side, and the compiler seems to be happy. I'm happy too. That's great. So that's how Apollo compiler works. All right. So that kind of took us through the demo portion of this talk. Next, I actually want to zoom in into the kind of what is compiler stages, what are the compiler process and what the compiler stages are, and then relate those back to our own compiler. You'll see this diagram a lot. I'll reference this quite a bit. So there's 3 different stages that we'll talk about. First is the lexing, then it's the parsing, and then it's the compiler bit. What the lexer does is it performs lexical analysis. What that means is that given a particular input, we want to make sure that all the tokens that we get in that input, all the characters we get in that input is correct. In the context of GraphQL, for example, a star character is not allowed. So when the lexer encounters that, it will bubble up and say, or it'll create an error and say, this character is not allowed. The parser performs syntactic analysis. What that means is that given the tokens that it receives from the lexer, what it wants to do is make sure they're in the right order, and then the statements it creates are correct. So let's say if we are looking at an object type definition, an object type definition must have fields. If those fields are missing, the parser bit will say, you're missing some fields. You're supposed to have fields. That is the job of the parser. At the end of it, it'll produce the type syntax tree, which is sometimes referred to as abstract syntax tree or an AST. What we then do with the compiler is we take that AST and we perform semantic analysis. What that means is at the end of this entire process, we just have an entirely valid program, if everything is correct. The type of semantic analysis that the compiler will do is it'll say, it'll check if the types in use are, for example, defined. If you're using a type that's undefined, it'll raise an error. It'll check if you're using the correct time in the correct type in the correct context. And if that's incorrect, it'll also raise an error. Those are the sorts of things it performs. So let's relate those back to Apollo compiler and how we manage our own kind of compiler stages within the project. So this is the architecture bit. So the first 2, the lexer and the parser, live in a crate called Apollo parser. We group those 2 together. The next bit, the compiler, lives in a crate, shockingly, named Apollo compiler. Those 2 projects coexist together. They're kind of sibling projects. Apollo compiler really depends on, or actually uses the AST created by Apollo parser. Lots of our work is based and is heavily inspired by the Rust Analyzer project. This is a language server for Rust that probably most of you are familiar with. It has been an incredible source of inspiration, and I'm super happy with how we've adjusted and adapted their process to ours. So let's kind of take a look at how exactly things are done. For the input data to tokens, what we do is very simple look-ahead parsing, where we just look through the characters coming in, produce tokens. The next little bit is we actually have a surprise visitor, and before we create the AST or the type tree, we create an untyped syntax tree. And what we do there is we actually use a recursive-descent parser. This allows us to have a super easy to maintain and really easy to diagnose code for us as people working on it to work with. It also allows us to be really, really specific about our errors, which is exactly what we want in a compiler that is meant to be diagnostics first. I won't talk too much about recursive descent parsing, but the blog post I was really inspired about is the one by Alexei Kladov called Simple and Powerful Prat Parsing. If you Google for it, you'll get a really good post on that. Let's talk about this untyped syntax tree a little bit. So what we use here is a Rust analyzers crate called Rowan. And what Rowan does is, or what Rowan is it creates this untyped syntax tree, or like we use it to create an untyped syntax tree. And what it is it's a red-green tree, but not specific. I won't talk too much about what a red-green tree is, but what it allows us to do is to be able to create nodes and have nodes reference other nodes and kind of have this relationship information without the types. That means that we're able to do this incredibly quickly and kind of do the recursive descent parsing in a very performant way. It's fast. But the question you're probably asking yourself now is, so how do you get to the type syntax tree? Because you want to be able to have Rust code to actually work with in an AST. And here we use another Rust analyzer crate called ungrammar, which is a domain-specific language, which allows us to quickly do a little bit of code gen beforehand and take the nodes that Rowan provides us and create a type syntax tree. This means kind of in a combination of the two things, when we use ungrammar and when we use Rowan, we can be quick with recursive descent parsing. We can have the benefits of having a diagnosable code and create errors, but we can also have the benefits of having a really easy to use typed syntax tree at the end. So it's fast, and you get an ergonomic API at the very end for your AST, which I really like. Another feature of our kind of compiler process is that it's meant to be fault tolerant. This means that we barely ever panic. There is a few times when we, for example, reach recursion limit and things like that. But in all other cases, we're able to gather errors and display them to the user. Let's take a look at this perfectly valid schema and mess it up a little bit and see what happens. So this is a perfectly valid schema. There's nothing wrong with it. But what we'll do is mess it up a bit. So this is a malform code. First of all, we have an unsupported character that elects or flags for us. And the second thing is we have a missing field type that the parser flags for us. But instead of panicking, as soon as we see something that's wrong, we gather all of our errors and all of our, and produce an AST still. So this is a debug output of our AST and errors. Having a fault-tolerant kind of parsing process allows us to return an AST alongside with errors, which ensures that the diagnostics that we then provide to the user are as comprehensive as we possibly can make them. This also means that we can walk the AST afterwards. This code is not really, it's more for aesthetic purposes. It's more to tell you that we can walk the AST. I wouldn't leave you unhighlighted code to look at. So we get the errors and we get the AST that we can walk in, and we can see all the diagnostics as much as we can, really, which is kind of the good way to go about it, in my opinion. The other thing is that we create the parser itself, and the compiler is lossless, which means we keep everything you send to us, like everything. For example, we have this very readable schema that's quite standard, but we can also have a schema that just has a lot of ignore tokens that we keep. We can also have a different schema that has a lot of ignore tokens that we keep. Keeping all the tokens and having a lossless parser allows us to be able to essentially reproduce back the input we get. That is incredibly useful for diagnostics. And yeah, so this is a debug output of the AST. We keep everything, including all the commas your heart desire to put into that schema. So let's say returning back to diagnostics, let's say we have this schema that is referencing a type that doesn't exist. Having a lossless parser means that we're able to then run it through and get an output that says, we are using a type that's not defined, and the type that's not in scope, but also exactly output your schema as it was, which means we're pointing to the exact location in your code where you had your error, which is exactly what we want to do when your code is malformed. Here are the commas that we wanted to put in. All right, I'm going to take a sip of water. It's kind of cool that we have like 3 compiler talks in one day at RustConf. It's very cool. I'm very impressed. Yeah, exactly. Everything is a compiler. Everything is a compiler or everything is a database. I'll give you that food for thought. All right, so we've talked about this before, but let's kind of brush up to it again. The 2 features of Apollo compiler is having an API to the compiler's database and the ability to be able to validate and provide good diagnostics in malformed code, or malformed GraphQL in our example. To be able to do number 2, we actually need to be able to do number 1 first. We need to be able to have that database and having kind of the relationship established. So the one thing that the compiler does is, given your GraphQL, it builds up the context and builds out the relationships between various types. What does that look like in the context of GraphQL? Let's take a look at the schema. This schema entry point is type query human. This human is a reference to a type human. A type human has some pets, and a pet there is a reference to another pet, and so on and so forth. There's references to different types everywhere. Those are relationships. We can also have a query. A query is a direct reference to the schema, so those are relationships as well. The first bit, the human, is a reference to the human in our type query. The name is a reference to the name field inside type human, and so on and so forth. So there are really a lot of relationships to be built out and lots of chaos. This is an artistic representation of my brain while working on this project. Welcome. And so there's a lot of types to build out as you build out the relationships and context. In fact, I think it's just types all the way down and then types all the way around, and you're just surrounded by types. But what that really allows us to do is to be able to have the context, the full context, so we know everything. And then the ability to provide an API to access those relationships. So here's a small example of how we're using it. We're creating the context, and then we're able to grab all the object types created. This is a smaller example. And then what we can do is just grab the name, individual name of that, of those object types. We can also grab the fields or the directives or the implements interfaces it uses, and all of that is sort of accessible. We can also find things in a database like the union or object type by name, by ID, by anything of that sort, because we have that full world kind of knowledge, full knowledge of the context. And that brings us to the database that I mentioned about 70 slides ago, and I'm happy you stuck around. Let's talk about the database. So all those relationships that we find out and we build out and we use are part of this last little bit of the compiler bit. What we use there is a project called salsa-rs, which perhaps some of you are familiar with, perhaps not. This salsa allows us to be able to create a database and ability to create queries for that database. A salsa is a generic, I've taken this from GitHub directly. Salsa is a generic framework for, So salsa is a generic framework for on-demand incrementalized computation inspired by Dapton, Glimmer, and Rust-C's query system. And I think the query system part is actually the more important one. So with the help of SalsaRS, we build out the database of our facts, and we also build out a query system that goes with that database. What do I mean by that? Let's take a look at like a small example of getting all object types from a given schema. We want to grab all of them. This is the query that does that. This is a query from our database that's backed by Salsa. What object type does is that it's a query. It calls another query that's called definitions. Definitions calls another, its parent query called document. Document calls parse. Parse calls input string. All of those individual ones are separate queries. What Salsa helps us do is that each one of these queries is memoized and is cached, which means if any one of these gets called again, instead of recomputing it, we just look for it in the cache, or Salsa looks for it in the cache. I don't physically do this, Salsa does this. So, for example, the definitions query gets used by multiple other different queries that's not just object types. It could be object types, but also input objects, operations, enums, interfaces. So after the first time we use it, all subsequent times, no computation has to happen, only a lookup in the cache. So this makes for a really performant way to create your database and allows us to play around, not necessarily right now, but perhaps in the future or anywhere around with this kind of query system. Not only is it performant, but it also makes for a nice interface of the database, of the API that's ergonomic. And what we do here is actually build out a database of facts. A database of facts that we can then use to be able to actually do the things that we wanted to do, like compose complex schemas, plan queries, do any sort of funky manipulations that we wanted to do, because we have this performant database and a database that provides us with an ergonomic API. But what this database really allows us to do, you know, when you do a data presentation, you kind of have to do the data phone, so this is the data phone. But what this database really allows us to do is to be able to provide diagnostics, because for us to be able to say, is this correctly used? Can we validate this? We need to actually have all the context of a given input, of a given GraphQL schema, of a given GraphQL document. So let's take a look at the schema and malform it a little bit. And so this is a perfectly valid one. We'll malform it a little bit and see what happens. We'll erase the pet, and we'll erase one of the fields inside type cat. So when we actually go in and want to validate this type cat, we'll go into our database of facts and see whether everything here is correct. In fact, it's not correct. As the message here says, an interface must be a superset of all interfaces it implements. What that means is that we have to have that field. And because we have this database of facts, we're able to actually check this sort of information and provide a user with a diagnostic that helps them fix it. When we go in to check for a type pet defined in various other places, after we've erased it, we're also able to do the same thing, check for whether that definition exists in our database, and create diagnostics that follow it. And these are just examples of the diagnostics we could create, but there's plenty more now that we have all of this information, and now that we're able to build out pretty much anything we want out of this database. So let's kind of take a breath. I'll have some water, and we'll wrap up. What did we talk about today? Today was a talk about ApolloRS. ApolloRS is a collection of crates. We specifically focused on Apollo parser and Apollo compiler, the two crates that allow us to kind of go through this compiler process stage. I know you're probably sick of this diagram. I promise it's the last time. So the two of them make up our compiler stages process. The input of our compiler is GraphQL, and the output is the database of facts. The two key features of the project are having this API to the database, an ergonomic API for that, that allows us to kind of access any of these types, any of these relationships that we want in a nice ergonomic fashion. But most importantly, being able to provide user diagnostics on malformed GraphQL code, which in fact, one of the design principles that we'd like to follow with this project is being able to replicate that Rusty experience that we know and love and bring that to GraphQL. And I think using the process that we've done helps us get there. And eventually maybe we'll even get more information out and get even better and better and better. And I think the possibilities are rather endless with this kind of database that we build out and this kind of compiler that we build out. We've built a lossless parser and a fault-tolerant parser, and we've built a database of facts that lets us ask all sorts of questions, but primarily what we're able to do is to create these really useful diagnostics that people should be able to use to fix their malformed code and have like good and functioning GraphQL. And these are, I'm gonna give a flash to Miet again, because this is gorgeous and I love the reporting library. All right, a few thank yous and acknowledgements. I wanted to thank my team my team and my partner and my cats who have helped me in the past year and a half while working on this project. As an acknowledgement, the beautiful font you've seen during most of the presentation is called Misto, designed by Katerina Korolevtseva. And the presentation slides are inspired by a combination of works by William S. Burroughs, E. Cummings, Tristan Tzara, and Louise Bourgeois. Thank you very much, and thank you for tuning in and joining me in the live audience.